two-dimensional salutations, fellow troglodytes. In this video, we'll have a go at making an ASCII Tesseract, a two-dimensional representation of a rotating four-dimensional cube, with a bit of an ASCII art twist. We'll not focus too much on the math, since there are great videos that do just that, but instead more on the fun bits at the end where we can tweak the way the rotating Tesseract looks and feels. So jump along and let's have some fun. Let's start our project in Visual Studio Code in a Python file, as we're coding in Python, by creating a virtual environment and then installing some dependencies. We're going to write python 3-m in our terminal and then the command virtual environment and give it a name, for example, .venv. That's going to create it, and here my Visual Studio prompts me to switch to that. So now the interpreter being run for my project should be this new virtual environment. We'll be doing our rendering in Pygame, so let's make sure we've got Pygame installed with pip install Pygame. We'll be using a bunch of matrix multiplication, so we'll be using math. So we can bring Pygame on board, bring some math on board, and let's get the operating system clock involved too. And then we will be using NumPy a little bit, so make sure we run pip install NumPy. Some interpolation. And let's import another thing called Bresenham. B-R-E-S-E-N-H-A-M. That's going to allow us to draw some nice ASCII lines with a bit more efficiency, as we'll get to. So then we can say from Bresenham import Bresenham. Those are the external dependencies we're going to bring, and I'm going to create just another helper utility file here called matrix, and we're going to do some matrix multiplication code here. I'm just going to paste it in. This is just an implementation of the mathematical operation of matrix multiplication, multiplying two matrices and returning the matrix product, where the restriction is that the number of columns of A must match the amount of rows in B. That's all that's doing. So we save that in matrix.py, and then we can import that too. Great. So now we've got our ingredients ready. Let's start defining some variables. So we're going to have our Pygame render the Tesseract. We're going to center the video, with SDL video centered being 1. Let's define the background color and the color of the bright color of the lines and characters we're going to display. So let's define two colors. Got some pretty dark background there and then the bright color, something greenish, perhaps red, green, blue at that ratio. And then let's define our canvas, width and height. Let's say that's 800, a square screen. We can initialize our Pygame and set a caption at the top of the window by running Pygame display set caption and then whatever we want. For example, ASCII Tesseract in my case. Lovely. And then set the screen display with our width and height, like so. We're going to take our clock from Pygame time. We're going to set FPS as well. Maybe it's 60, which we're going to pass in later on. Now I think we could put in some of the fonts I want to use for the ASCII RT bit. Let's say we've got one font for the lines that we'll draw between the corners of the hypercube. So let's take Pygame font. There's a whole array of system fonts you can pick from. You can set these to be anything you like. I picked one for the lines called Scheherazade, and let's have another one for the corners, so we can have some visual interest in our hypercube. Same deal, Pygame, font, sys font here, maybe another font here, and maybe a different size by default, and also bolded to make the corners pop out a bit. So that's going to be our ASCII basics, which we can tweak around and play with. And then something about the Tesseract information. For example, the angle at the start of the rotation, 0. Let's make sure then that it's going to be at the center of the screen. I'm drawing on existing code I'll link to in the video notes here. So whatever the width and height of the screen is, we're going to just grab the middle point. And we're going to apply a scale value to scale up our cube and set a speed. I'd set it at 0.005 in the demonstration there. And then we're going to define 16 points because that's what we've got in the Hypercube's corners. If a three-dimensional cube, a regular projection has 8 corners, we are going to need 16. So let's define the array here, and then we can do the boring part of pasting in all the permutations. So we've got between -1 and 1 and 4 dimensions, 16 permutations, covers it all. Okay. What we could do next is create the basic Pygame loop, where we're going to be playing. So it's going to run. While it's running, we're going to have the clock ticking. We're going to run through these iterations at the FPS rate, ideally. We're going to fill our screen with the background value we've defined up above. And then let's define some Pygame keyboard commands that will be useful. If the event type is Pygame quit, then the running will cease. Lovely. And if, let's keep up. Press escape, then it's also going to end. Access to me. And then at the end, we'll be updating the display at the end of each loop with whatever points we've gone then. We've got quit there at the end. So that's going to be our basic game loop. And now we get to the mathy bits, I think. Which we won't go into that much depth with, but let's go. We're going to start our indexing from 0, and to go from 4 dimensions to 3 dimensions and 3 dimensions to 2 dimensions, we're going to run some projections, and that's going to happen with some matrix mathematics, with identity matrices, and I am only going to copy paste the ready rotations for the 3D matrices and 4D matrices. Here's the 3D. Rotation for X. We've got our cosines, negative signs there for Y. That's that. And for rotation Z, we prep it by taking whatever the angle is. So those are the rotations that will be applied. Tesseract rotation. And the fourth one is that one. For 4D math rotations, it is left as an exercise for the reader to memorize these by heart for your own nefarious purposes. rows and 4 columns for those matrices. And then we can start looping through the points once we've got our rotations defined. So to get the rotated 3D, we run a matrix multiplication on 4D rotation for x and y around a certain point. So we'll take whatever that point's position as a matrix is and multiply it with this 4D xy rotation in this case. And then take that one and rotate it again on the other axis here, so W. And these could be swapped around if you want to change the direction how the cube rotates. We're going to define a distance, and if we think of the three-dimensional cube's dimensions as x, y, z, we get W as the label for the fourth dimension. We can then define the projection matrix. How do we get from this identity matrix from 4 dimensions to 3? And that happens again by using our matrix multiplication. We take the rotated 3D cube and matrix representation we've gotten from here, and we run it through the projection matrix so that we end up with a projected 3D matrix. And then we kind of take it lower down, another dimension, since we've only got 2 dimensions on our screen to work with really. We take the projected 3D matrix and run it through the Tesseract rotation. Similar step. Z. We get our rotated 2D matrix projected when we take our matrix multiplication, the rotated 2D matrix projected again, and then we can grab the x and y coordinates for this point when we scale it up and add it to the cube position. If we think the cube is centered, we then take that 2D projection, apply the scale multiplier, and add it here so we don't render it in the corner or anything. And then we can start filling in our projected points array and say that here we have x and y. This is what we're going to use to position our line dots on the screen. We could conceivably also pass the other dimensions if we want to try and display those somehow with changes in color or intensity, for example, or maybe the symbols that we display. And then we're going to iterate and increment the index. And then we can think about drawing the edges. So this gives us our projected points each step of the way. Using these projected points, we can then create lines, draw the edges, but we need a method to actually connect the points. So let's define that up above, skipping this quite rapidly so we get to the ASCII bits. We will have this method for connecting points. We take the I and j, and we're going to define a as whatever is k times I and B similarly with the J plus offset. And here the line will be whatever the Bresenum algorithm gives from the x0 basically and x1 and the y0 and y1 coordinates. So if we just stop a little bit and think what we're doing here, or maybe more simply what we would be doing with the corners, we'll be passing in the line points. And here we want to have a line represented as points so that we can replace some of those points, or render some of those points as ASCII characters, as we saw at the start. So then we can maybe implement a skip value for however many of these points that we get in our array. We only want to render, so let's say we only want to render every 7th point. We can say that for each point in this line that we're getting from the algorithm, we will only render every 7 steps of the way. And then we're doing the rendering there. Otherwise, if it slips below, let's reset our counter to whatever the skip value is. So now this is where we would display our ASCII character every n steps. So let's make sure we've got a method for that too. Take a letter, and it's going to be put in X position and Y position. And we could here say the text is whatever our line font is that we defined at the start. We're going to make sure that whatever we've passed in as a letter is a string. We're going to anti-alias it, and we're going to give it a color. In this case, whatever we defined is the bright color. And then we're going to blit it to the screen. So it's this text variable, and it's going to be at the position we just set. So that's going to be enough to draw it on the screen. We just need to call it here in connect point then, and say text display. It's going to be some ASCII character. We can define that. We can actually pass it in, can't we? Let's just say it's this one there. Line character. I used a colon in my demonstration. I think it worked pretty nicely, but this could be many. This could vary. You can get creative with that. Let's just say whatever the line origin is will be that. 0.0 to 0.1. So now we're going to get a fairly efficient line of points from as integers from the initial between the start and end point. And just briefly, the Bresenum algorithm is one that gives integer coordinates, and the algorithm avoids doing floating point arithmetic. So given the amount of calculations that a rotating cube, hypercube necessitates, this is a better, more efficient solution that we want to be implementing early on. Right, and then we can jump back to drawing our edges, where we now have our connecting point method defined, and we take our 16 points and handle them appropriately, and also increment our angle with whatever the speed we've defined up top is, and then display update. So now if we were to run this, it should give us the lines of the Tesseract. Let's give it a try. I'm going to run this, see what errors come up, run the Python file. And there we have it. Rotating Tesseract with colons, drawing lines. between the 16 points. Splendid. That's already making me pretty happy. We could cycle the colors, we can change the rotation direction and the width by changing some of this stuff, the math, the order of rotation operations, for example. And we can use another character. I wonder what else would work as an ASCII character. Instead, what would the letter O look like? Groovy, pretty hypnotic. Okay. Splendid, splendid. Turn that to colon. And let's see if we can tweak this a bit more by adding some corner points. So we know what those corner displays are. If we just say that at the end, if we are not looking at the projected point index, so we're cycling, we're just saying corner display, calling a new method, passing in x and y, and defining it here to render something different at the corners. So we could say, instead of connect point and text display, below that, a corner display. And there we can say something about how to define that. We can say whatever the corner font is, we'll render again a big capital O in our bright color. And let's see how that looks. So then we get some nice fix points for our eyes to fixate on, and we can start getting more creative with our ASCII dimension of our cube animation. So what could we do? Now we could represent perhaps the Z and W dimensions in some way. We could swap around the ASCII characters, and we could maybe change their brightness, change their color even, interpolate between different dimensions of data. So I want to leave that pretty open to you, how you might take this little experiment and take it further, but I'll show you an example of or two of what I had in mind. Next. So here in corner display, we could make it richer by saying, what if we pass in our Z and W variables too, make sure we pass them in when we call the method there, and then do something with that. So we could interpolate the color first of all. So we've brought in our interpolation operation. So we can define a interpolation between the Z value and our background color and brightness, for example. That's going to be a bit of a monstrous line, I think. We can say our interpolated color value for any point at any given time is whatever the interpolation of the Z value between, I've tested this a bit, whatever kind of values between that range more or less, and then we map it from those input values. So we're getting a Z value, let's say it's 0.2, we know it's going to be roughly within those bounds of 0.1 and 0.3, and we can say, okay, if it's close to 0.1, then we're going to render it the color of the background, so very dim, background color 0, and if it's very high the value, we will render it with whatever we've got in the bright color. You can pass other colors here too if you want, and do the same thing, interpolate per 1, GitHub Copilot to the rescue. So we're doing the same thing 2 more times, for 1 and 2, to get a new RGB value for interpolated color. And here we could say, instead of just bright, we could say interpolated color. And maybe we'll have a variable here saying interpolated, if we do want to do this interpolation. If interpolate color, else I have to give it some value. It's just bright. Okay. Aha. So now we see that the brightness alters based on whatever the pass-through Z value is at any given point. So getting a bit messier here, but also a bit more pondering if you really want to think about the different values of the corners and what's really happening when a four-dimensional cube is rotating in two-dimensional representation. So that's one way. You can interpolate the color, and you can maybe interpolate the size too. Let's do that by the other W dimension, just to add some more zaniness to our ASCII Tesseract. So if we've got our color interpolation, let's say our font size interpolation is also a thing, and here we can say, in that case, that we'll be interpolating W in font size. And here we can say then that if we are indeed doing that, then the font size will flip between those values and something great, so enlarge. Maybe something like that from my example. But we then want to adjust the font we've defined to have the size that we're just saying it should have. This font size should be applied. Let's see how that works. And then what I've done though is I would be subtracting the font size to make it look less ugly, and these are little hacks that you might want to do to make things look nicer, although certainly are pretty. Let's change the thing we're rendering to just a period. And it's looking pretty squat. Okay, now we have some cubes that work nicely with the offset and the sizings I've chosen. So now we are actually there where we started in the Tesseract I was showing at the beginning. And the size does alter. Small in the middle, small when Z is small. But then let's revert this back to being W as we said it would be. And now, in theory and in practice, we are visualizing all four dimensions somehow. The projection, but then the vertices also inform us something about the Z and W dimensions as they are at that level of projection with their size and their brightness. You could go wilder, change the ASCII character, change the color, have a color rotation, maybe periodically change the way this rotates. Everything is possible now that we've rushed through the code to have your little ASCII art rotating Tesseract. Well, hopefully some of that was something you were able to follow along with. We'll be posting some links to better explain the math behind this, and many thanks to the people writing the code I've referred to pretty heavily in this video. Let me know if you had fun with this and what else you might want to see. With that four-dimensional cube now inside you, be sure to have a great day, and I will see you later.